also known as what? And that's going to be the clearance, okay? So how fast that substance is coming out in the urine is the clearance rate. We talked about what micturition is, basically urination. The glomerular filtration rate is the rate at which the substance is being filtered across the glomerulus, right? So movement across the glomerulus from into the Bowman space. And then the transport maximum was the rate at which movement was taking place or transport was taking place across the epithelial cell at which all the carriers were maximized or saturated, okay? And then we also talked about the renal threshold, which is not here. The renal threshold, to distinguish this, is the plasma concentration at which we start to see spillage of whatever substance into the urine, okay? We talked about glucose as an example. The plasma concentration at which we start to see glucose in the urine was actually about 160 to 180. Okay. All right, let's look at another one here. Okay, which of the substances has a zero clearance rate? And I think we mentioned this when I looked at that table, but glucose, we said, should not ever come out in the urine. Glucose should be 100% reabsorbed, and so its clearance rate should be 0. And we compared this to something like inulin, which had a clearance rate that is exactly that of our GFR, and so that is neither reabsorbed nor secreted. Okay, so the answer here was glucose. Okay, let's see if there are any questions that came up. Otherwise, we're going to move on to packet 2, which is renal balance, part 1. And so as you'll see, most of what we're going to talk about going forward is going to build on everything we just talked about. We're going to go into a little bit more detail about the different parts of the tubule and talk about how the kidneys maintain balance, maintain homeostasis with regards to our water balance, our sodium and potassium balance, and our acid-base balance, okay? And so that's why the remaining packets are called balance, right? We're talking about the different aspects of balance that are brought about by the kidneys. So, let's start off with this first one. Our objectives here are to explain the concept of balance, describe the different sources of body water input and output, and then explain the control of water balance and osmolarity by antidiuretic hormone, or ADH, or vasopressin. Those are all the same hormone, okay? And just to kind of go back to when we talked about this hormone last semester, this is one of the posterior pituitary hormones. Remember, it is released from the posterior pituitary and it has its action in the kidney. So we're going to kind of pick up from what we left off talking about in the endocrine system and talk about how it actually brings about its function at the level of the kidneys. Okay, so you can make a note that this is also called ADH or vasopressin. And just to be clear, when we talk about osmolarity, this is often a term that students kind of get confused. Osmolarity is the solute concentration of the blood, okay? It's going to be a representation of how much solute is in the blood, mainly sodium. We're talking about mainly the sodium concentration in the blood. We talked about isoosmotic being the relative osmolarity compared to the blood, and that was usually about 300 milliosmoles. That is the osmolarity of our plasma. And so we're going to talk here about how osmolarity is regulated via the kidneys. Now, all of this kind of falls under the umbrella of homeostasis. So homeostasis is this idea of keeping the body in balance, right? Keeping things at a steady, constant value when it comes to our blood pressure, temperature, pH, and all that good stuff. But when it comes to water, this is really involving the kidneys. So homeostasis here means keeping the water inputs to our body and the production equal to the water outputs and the utilization. So in order for our body to be in balance, how much we're bringing in from sources like our food, from sources like just drinking water, and how much we're producing, how much our cells are putting off. Remember, as a byproduct of cellular respiration, a little bit of water is produced. That should be equal to how much we're utilizing for body processes and how much we're outputting via the kidneys, okay? So in order to be in balance, those two sets of variables should be equal or at balance. So the kidneys regulate the the solute and water content, which determines the volume of our plasma. And it also regulates the acid-base balance. We talked about how the distal parts of the tubule secrete hydrogen ions. We're going to talk about how the proximal tubule reabsorbs bicarbonate. And so via those two mechanisms, the kidneys can help regulate our acid-base balance. And you would have talked a little bit about acid-base balance as it pertains to the lungs, but also understand that the kidneys play a role in balancing out in more of a long-term way than the lungs do. The kidney is also involved in exchange between different compartments. So we know that we have various body compartments. We've got our cellular level, which is water that's inside the cell, the intracellular compartment. We've got water in the connective tissues. We've got water involved in our GI tract that's coming in through the diet and the food that we eat. We're losing water through sweating, through the skin. We're also losing some bit of water through humidification when we bring in oxygen, during respiration, I should say. And so in order to humidify the air that we bring in, a small amount of water is donated to that. So there are different areas that are involved in water balance. So not just the kidneys, but the kidneys are kind of the main one in terms of regulating the overall balance. So let's talk about the sources of water input and output. So when we ingest food and water, it comes into the digestive tract. We also have cells that are, according to cellular respiration, they are producing some amount of water. We have water in our connective tissue, so in our bones, in our blood, which is a form of connective tissue, in our cartilage. That is also an area that is contributing water to our overall plasma. And so all of those are some of the water inputs. The outputs are going to be obviously excretion. So we lose some water in the feces, we lose some water via sweating, if we're bleeding or hemorrhaging, via humidification of air, so via respiration, and then through the kidneys via urine, right? The excretion of urine is a major way that we lose water there as well. So in between the water that is moving into our plasma, into our blood through the inputs, and urine specifically, there are the three exchange processes that we talked about so far. Filtration, which is filtering that plasma, secretion, which is secreting substances and water into that plasma, and then reabsorption, which is reabsorbing water and substances back into the plasma. So these are the exchange processes that are really going to determine how much urine is excreted. So as we can see here, the kidneys are really regulating the water output and so play a major part in water balance. Okay, so let's kind of describe this idea of balance here a little bit, and then we'll talk about some of the organs involved. So solids in water enter and exit the plasma at the same rate. That is a state of balance. That's where the body likes to be. That's homeostasis. And so we can think about that as this first beaker where we have water input and water output exactly equal, and there's no change in the volume of water. In a state of positive balance, water or solute is entering the plasma faster than it is exiting. And so the concentration is going to increase, the water balance is going to increase. And we can see here that the volume is going to increase, right? So as more water is entering than what is exiting, we end up in a state of positive balance. And then a state of negative balance would be the exact opposite. okay? Solutes or water are exiting the plasma at a rate that is faster than that is entering. And so the overall volume would decrease and we're said to be in a state of negative balance. Now, while we're talking about these as beakers, I want you to kind of think about this in terms of the human body, the entire human body. And so a condition or a scenario that's synonymous to negative balance is dehydration. If we're dehydrated, there's less water inputs than there are water outputs. And so our overall volume goes down and we're said to be in a state of negative balance. If we're overhydrated, and we'll talk about what the term for this is, but the opposite is happening. The opposite is true. The input is greater than the output, and so we're said to be in a state of positive balance because of that. So let's talk here about solid and water balance in the distal parts of the tubule. This is mainly regulated in the collecting duct and the distal convoluted tubule. And so there are two cells that are found here. I kind of mentioned them earlier, the principal cell and the intercalated cell. And these are the cells that are involved in regulating water and electrolyte balance. So these are the cells that are going to be sensitive to hormones like ADH, and other hormones that I'll talk about, but these are the cells that are going to decide whether or not more water should be reabsorbed or solutes, or whether less water and solutes should be reabsorbed in response to our overall body status, in response to our overall body hydration. And this is what I really mean when I talk about the distal part of the tubule being regulated. So if I'm well hydrated, the distal parts of the tubule, under the influence of the hormones, will reabsorb more water if I'm dehydrated. If I'm well hydrated, they'll reabsorb less water. And so that can be manipulated by the principal and the intercalated cells. The intercalated cells more so with the acid-base balance. So that's going to be the secretion of hydrogen ions as a part of balancing our acid base. Okay, let's move on to objective 3 to explain the control of water balance and osmolarity by antidiuretic hormone. So this is that hormone that I was talking about earlier, and we'll talk about how it affects the osmolarity and the movement of water. So water reabsorption, actually, let's skip over this slide. This is just the topics that we're going to talk about. So when we talk about this state of balance, although we were speaking about it in terms of the beakers, this is what it actually looks like in our physiology. So the inputs, which I mentioned earlier, things like ingestion, things like what's produced from cellular metabolism, and then the outputs are things like excretion, things like insensible loss. And when we say insensible loss, we mean sweating, sometimes speaking, right? Saliva comes out of your mouth, coughing, you humidify as you speak. That is an insensible, like a small amount of loss. And then urination, which is probably the most of that, about 1.5 liters per day. And so we talked about the fact that these water inputs and outputs should be balanced, okay? So if you add up the total inputs, we got about 2.5 liters per day. And if you add up the total water outputs, we should also get about 2.5 liters per day in order for the body to be in balance. And if we do that, we end up in a state of normovolemia. So homeostasis is synonymous with being normovolemic or having a normovolemia, normal amount of blood volume. But if you are in a positive water balance, the physiological term is hypovolemia, meaning you have high blood volume because your water inputs are exceeding your water outputs. And if you have low blood volume, being in a state of negative balance, this is called hypovolemia. And this is synonymous with, again, dehydration, hemorrhaging, shock. And this is where your water inputs are less than your water outputs. So your water outputs exceed your water inputs, okay? All right, so water is moving down its concentration gradient. This is called osmosis. So in order for water to move anywhere in the body, we talked about water movement before, it must move according to a solute gradient. And so we talked about transport, I think in one of our units last semester, we talked about this idea, for example, the creation of saliva. Saliva or mucus, any of that type of water movement, a solute gradient must be set up first and then water can follow. So if you have a high to low solute gradient, you have a low to high water gradient. And so the reabsorption of water will happen passively according to the solute gradient that's been set up. So that's how water moves everywhere throughout the body. Anywhere that there's water movement in the GI system, in the kidneys, it is happening according to that principle. Solutes move first and then water can follow. So let's talk about how the osmolarity changes throughout the different parts of the kidneys. So typically we start off with an osmolarity of body fluids being equal to the osmolarity in our tubule. So in our plasma, the osmolarity is about 300 milliosmoles. That's what we call isosmotic. And so there's no osmotic force to move water under that circumstance. So the kidneys have to create a mechanism where they create some type of solute gradient first, and then water can follow passively according to that osmotic or solute gradient. And that's what we see happening here in various parts of the tubule. So this is the proximal tubule. So the proximal tubule, 70% of the filtered water is reabsorbed. We said that this was not regulated. This happened freely. We talked about the various adaptations that allow this type of unregulated reabsorption. In terms of the water reabsorption, the distal parts of the tubule and the collecting duct, it's going to be regulated. It's going to be under the influence of external factors like the hormone ADH and in some regard the sympathetic nervous system. But this is what we mean when we see that it is unregulated in the distal tubule. It's happening under the influence of our hydration, of our hormones, and external factors. So let's talk about water in the proximal tubule. And we spent quite a bit of time speaking about this in the previous packet. So I'm going to kind of skip over this a little bit. But the basic premise of water reabsorption in the proximal tubule is that sodium was actively transported across the basolateral surface by the sodium-potassium pump. Chloride was attracted passively because of that pumping of sodium. And then because of the movement of both of those solutes, water simply followed by osmosis. Okay. So I'm not going to go over this again. We talked about all of this, how sodium moves, chloride moves, and then water simply follows. So we're going to skip right over that. That's what happens in the proximal part of the tubule. Let's look here at what happens in the loop of Henle. So in the loop of Henle, there's this interesting phenomenon that's called the medullary osmotic gradient. And the medullary osmotic gradient is a gradient of the osmolarity from the cortex down into the medulla. Remember the anatomy here. The loop of Henle is dipping from the cortex down into the medulla. And so what we also see here is that there's a gradient happening between there's a gradient of the solute concentration happening here as well. And so closer to the cortex, the osmolarity is less, right? It's lower. But as we get down into the medulla and we approach the renal pelvis, which is kind of the center of the kidney, the osmolarity is drastically higher. And this gradient of the osmolarity is critical to the water reabsorption that happens along the kidney, okay? So we're going to spend some time talking about how this is established, but basically we have water reabsorption happening down the descending limb of the loop of Henle and solute reabsorption happening up the ascending limb of the loop of Henle. So as we go from the glomerulus to the proximal tubule, to the loop, to the distal tubule, to the collecting duct, remember this is the direction of fluid, we have water that the filtrate that's here, that's what I'm calling water, that has an osmolarity that is the same as our plasma. And so under that circumstances, we won't see any movement of water. So as we go down the loop of Henle, there's this opportunity to set up a gradient that can allow us to move water. Okay. So because the descending limb is permeable to water, but it is not permeable to other solutes, only water moves across the descending limb. And because the ascending limb has the exact opposite, it is permeable to solute sodium, potassium, and chloride, but it is impermeable to water. We can only move solutes down the descending limb. And that difference in the anatomy, that difference in the permeability of the different part of the loop is what is responsible for setting up the medullary osmosis